Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up, and don't forget to subscribe. We will see you in the next video, and thank you for watching.
Today our lesson deals with finding the composition of compounds. It starts on page 162 and it ends on page 172 from the text, Chemistry 11 in Focus. And we'll be looking at how you find the percentage composition of compounds, finding the empirical formulas for compounds, and how the empirical formula of compounds can be determined experimentally. And then we use the information gained there to find the molecular formulas for compounds. Before the usefulness of any compound can be evaluated, its molecular composition must first be ascertained. This chapter discusses how the empirical molecular formula of simple compounds are determined based on the elements present and their respective percentage compositions by mass in the compounds. The percentage composition of compounds by mass not only leads to the determination of their molecular formulas, but it is also useful in making comparisons of the percentages of the same or different elements in different compounds. For example, nitrogenous fertilizers are made and sold in different forms, such as potassium nitrate and ammonium sulfate. Knowing the percentage composition of each element in these compounds by mass would allow someone to choose which of the two will be more suitable to replenish soil that is depleted of nitrogen. Of course, we know nitrogen can be found in these compounds here. In the case of treating anemia, it is important to know the percentage composition of iron in a supplemental compound such that the correct amount of it can be safely administered to patients. By knowing the molecular formula of a compound, its molecular geometry can be determined, which in turn can be useful in deducing its chemical and physical properties. Knowing these properties can provide useful information about the compound's ability to change into more useful ones. More importantly, molecular formulas of compounds lead to the calculations of their molar masses, which is essential in stoichiometry. The compound ethene, for example, has the following features. Knowledge of these is important in its combustion and other chemical reactions. So here are some features of this compound ethene here. It's an alkene, and that's the formula here. And this is its empirical formula. We talk about that. You can see this is the smallest ratio of atoms in this compound here as a molar mass. So you can see, look, you hold this and put it inside there. It's half of that. So the molecular mass will be twice what that one there is. The law of definite proportions. Scientists have discovered that compounds contain elements in fixed proportions by mass. Regardless of how many different samples of the same compound are analyzed, results show that the elements in each different sample are in fixed ratios by mass. French chemist Joseph Louis Proust, having analyzed various samples of copper-2 carbonate, found that the elements copper, carbon, and oxygen were always present in the same proportion by mass. He formulated his law of definite proportion, which states that in any specific compound, the elements are always present in definite proportions by mass. So that's the law of definite proportions. is telling us doesn't matter where you analyze the same compound, you'll always find that the elements present in it are in definite proportions by mass. Now I want to introduce to you how you find the percentage compositions of the elements in the compound. But first of all, we use marbles to show how that can be done. Let us suppose in a box you have 20 blue marbles, 30 red ones, 10 white ones, and 40 black ones. And someone asks you to calculate the percentage of each different colored marbles in that box. What we'll do, we will find the total number of marbles, which in this case is 100. Then what we do, we take each colored marble and put it over the total and multiply by 100%. If you do the percentage of blue marbles, it will be 20. We have 20 blue marbles here. So you divide 20 by the total number of marbles there, and you multiply by 100%. And you get this value here. You want to know red marbles, where you have 30 red marbles there. So you divide the same thing here, 30 by 100. You end up with 30%. White marble, you put 10, you have 10 white marbles there. You take that 10, divide by 100 here, and you ended up with 10%. Then you have now black marbles, which are 14 black marbles there. Divide by total number of marbles, which is 100, multiply by 100%, and you end up with 40%. When you add all of these up together, you must end up with 100%. We use the same strategy now to see how we can calculate the percentage composition of the various elements in compounds. You want to find the percentage composition of these elements, sodium, oxygen, and hydrogen in sodium hydroxide. So the first thing we'll do, like what we did for marbles, we'll add up all the molar masses of these and see what it tallies to. So in this case, the molar mass of sodium hydroxide here is 40 grams per mole. Then we will do what? We will take the mass of each element here and put it over the total like we did for marbles. In those cases, the number of marbles added up to 100, but here the mass of the elements here added up to 40 grams. So you take it for sodium, what sodium is, put it over the mass for this entire compound, and you multiply by 100 there, and you end up with 57.8%. For oxygen, you do the same thing. Take the 16 there, put it here, divide by the molar mass, times 100, and you get that guy there, 40%. Hydrogen, you do the same thing, and you end up with that there. When you add all of these up together, you should end up with 100%. In any sample of sodium hydroxide, any sample, doesn't matter, small one, big one, whatever you do, the percentage composition of sodium will be 57.48, oxygen 40.00, and that small amount there is hydrogen. Any sample of sodium hydroxide, doesn't matter which part of the world you take it, you'll find these percentage compositions for the various elements present in. Same thing we can do for calcium hydroxide. Now you got to watch here. Now we talk about this radical here. So be attentive to these radicals when you're going to calculate the molar mass for these compounds. Here you only have one calcium, so you're going to have calcium is, you know that, stated 40 grams per mole. But because everything in these parentheses must be multiplied by 2, that means you're having two sets of hydroxyl ions, okay? So it means that you're going to have two sets of oxygen and two sets of hydrogen. So you have 2 moles of oxygen for every mole of this. So you take 1 mole of oxygen times 2 moles, you get 32 grams there. 2 hydrogen, same thing for hydrogen here. And you end up with that mass there for your sodium, for your calcium hydroxide. Then you do the same thing now. What we'll do, you take each of these, put it above this one here, and you multiply by 100%. So this is it for calcium. You end up with this, oxygen 43.1, hydrogen this. You're taking, and in the end, if you add up all of these, it should be equal to 100%. So that is the percentage composition of calcium, oxygen, and hydrogen in any sample of calcium hydroxide. And then you have some questions here. Solutions to these are in the manual, solution manual. Next thing is empirical formulas for compounds. If you look at this table here, it is showing you different compounds. You get a name here, dinitrogen tetroxide. This is glucose. This is ethene, the one I showed you before. This is water, sodium carbonate, benzene, and nitrogen dioxide. The empirical formula of a compound is the smallest ratio of the elements in that compound. For example, you're having N2O4. What is the lowest this can be reduced in terms of number of nitrogen and oxygen? You see, this is what it is. The smallest ratio of the atoms in this compound here, right? And you can see the ratio of the atoms will be 1 nitrogen to 2 oxygen. That's the smallest ratio you have there. This one here can be broken down to, if you divide everything by 6, you'll end up with CH2O, a hydrate of carbon. That's what's called carbohydrate. And now you look at the ratio of the elements there, it'll be 1, 2 to 1, 1 to 1. Ethene. Ethene can be reduced to this. It's 1 to 2. Water would not go further than that. This one will go further than that. This one, now you divide by 6, you end up with this. And of course, this doesn't have any smaller one. It is the same. So this is what is meant by the empirical formula. Next, we'll be learning how to find the empirical formulas of compounds. Let us say someone gave you the following percentage composition for the elements in a compound. That is it for hydrogen, that is it for sulfur, and this is it for oxygen. So what we'll do first of all is to change these into masses. What this means in a different way is that if you have 100 grams of this compound, you will have 2.02 grams of hydrogen, 32.65 grams of sulfur, and that 65.31 grams of oxygen. So the first thing you do when you're given a problem like this, you change percentage composition to mass of each in grams. So we change 2.02% to 2.20 grams, 32.65% go to 32.65 grams, 65.31 percentage is changed to 65.31 grams. That was what is going to be found for these in 100 grams of the compound. We want to know the ratio of the atoms in the compound. So the most accurate thing to do is to find the number of moles of hydrogen in that, number of moles of sulfur in that, number of moles of oxygen in that. First step, we change all of these to mass in grams. The next step will be to find the number of moles of each element present. So you divide that by the molar mass for hydrogen. You divide this by the molar mass of sulfur, and you divide that by the molar mass for oxygen. When you do that, you end up with these values here. But because we do not have nice whole numbers, we do not have 2, we do not have 1, and we do not have 4, nice clean whole numbers, we are having some decimal points there. Do not round off at this point because your answer will not be accurate. So what we do, we try to see how we can get rid of these decimals and end up with whole numbers. So the next thing we'll do to get rid of the decimal, you divide each of these here, that one there, and this one there, by the one that is smallest. And this number here is the smallest one. So this is the next step. Dividing each of these by the same one here, smallest one here, we now end up with whole numbers, nice whole numbers like these. Okay, these are the whole numbers. It means that in the compound, these will be a number of atoms present. So you have 2 hydrogen atoms, 1 sulfur, and 4 oxygen. So what we do now, we make these the subscript in the formula. Hydrogen there, you put it 2 here. Sulfur is 1, you don't put it, and oxygen. So this is the empirical formula for that compound there. So quickly, one quick review. If you're given the composition of all the elements in a compound expressed in percentage, change that to amounts in mass, each of these. Because you're assuming that if you have 100 grams, this is how hydrogen will be represented, and so on for the others. Next thing is, you divide each separately by the molar mass of each of these. That's not difficult to find from the periodic table. Then you get these values here. If you find that you're having decimals, don't round them up. Divide each of these by the smallest value there. And the smallest value there is the one for sulfur, 1.02. And here now you're getting these now. Now you round off at this point here. You round off at this point, okay? But you try your best to get rid of that. So it didn't work out well. So now you round it off. After that, then you can round off now. So it's H2SO4. Now you get in a similar one like that again, here. So what do? Change this to what? Change percentage composition to mass and grams. So this is it, that is it. Next thing is, we divide each of these by the molar mass for these elements. That is it for carbon, chlorine, and fluorine. You now end up again with decimals, right? So we do not round off at this point. You get erroneous results. So we take each of these now for the next step and divide it by the smallest value here, which is 0.910. So having done that, we ended up with nice values here, nice round figures here, but we still ended up with a decimal of 1.50. So to get rid of this now, we multiply everything by 2, because by multiplying this number by 2, we end up with a whole number of 3. So if you multiply every one of those here by 2, see, you multiply this by 2, it gives you 3, this becomes 2, that becomes 6. So these will now become the subscript in your formula. So you take this 3 and put it there, you take this 2 and put it there, and you take this 6 and put it there. So this is your formula here. So you might want to ask, if you have decimals like that in the end, how do we know what value to multiply by? So let's say you ended up with decimals like these, right? 1.2 for one of them, 2.25, and so on, right? What number to use to multiply these so that you end up with whole numbers? There's a table here is given to you. See, this one here, see, it has a 0.2 here. If you multiply this number by 5, you end up with 7. What about if you have 2.25? What will you multiply this by? You multiply this by 4, okay? What about 0.33? That can make a whole one if you multiply by 3. What about this? 5, 2. Can't figure out that one right away now. Let's maybe 3 or something like that. Let's see. Yeah, 5, almost 5. So these are the decimals there. If you encounter these decimals here, after you've done your second division there, okay, you multiply each of these by these factors here, okay, and you'll end up with a whole number. But when you multiply decimal, you also multiply all the others too, as I've shown you.